Palm Jumeirah really was made to sink, just not underwater. Before the main construction began, 15 cranes worked through 200,000 points across the areas set aside for building, driving vibrating probes up to 12 meters into the ground. The sand packed tighter, the surface dropped, and crews poured in more sand, and did it again. That brought forward much of the settlement that might otherwise have continued naturally for decades. Dubai made the ground settle early, so it would move less once the buildings were in place. But why was the ground under a future city that unstable? The island under your feet on the palm is not bedrock and not a concrete slab. It is sand, lifted off the floor of the Gulf and placed into the sea. When sand is placed into water, the grains land loosely. Below the groundwater line, the gaps between them fill with water. But the problem is not that this water needs decades to escape. Clean marine sand drains fairly quickly. The problem is the structure. Under the island's own weight, under construction loads, and under repeated vibration, those grains keep rearranging into a tighter arrangement, and the surface goes down with them. Note what is happening. The sand does not disappear. The number of grains stays the same. What changes is how tightly they sit, and therefore how high the surface stands. If that happens after the buildings go up, and unevenly across the site, you get differential settlement, roads, pipes, and foundations moving by different amounts. So the sand had to be compacted deliberately before the main construction. The method is called vibrocompaction. A long steel probe is lowered vertically into the ground, a vibrator oscillating horizontally. To get it down, water was pumped under pressure from its tip, loosening the sand beneath it. At depth, the real work starts. The horizontal vibration weakens the frictional contacts between the grains. They are free to shift, and they rearrange into a denser packing. Pore volume falls, and the displaced water moves upward and outward. The work is done in stages. The probe treats one level, then rises a little and repeats from the bottom up. Around the probe, a column of compacted ground forms, and the surface above sinks into a crater. That crater is filled with sand, and the probe moves on. Now the scale. Roughly 200,000 points. Treatment up to 12 meters deep. 15 cranes. The bulk of the work on the trunk and the fronds was finished by July 2004, while work on the crescent continued afterward. Afterwards, the surface was leveled and rolled, and density was checked against defined engineering targets. The ground had to reach specified values, not simply feel firmer. And there was a second reason for all of it. Loose, water-saturated sand is dangerous for more than settlement. Under strong shaking, it can temporarily lose bearing capacity. Poor water pressure rises sharply, the grains stop resting against each other, and the ground behaves like a thick liquid. That is liquefaction. The tighter the packing and the smaller the pore space, the lower that risk. So the compaction solved two problems at once, bringing forward a large share of the potential settlement and reducing the chance of liquefaction. But all of it depended on having the right sand, and that part was a surprise. Dubai sits in a desert. You would think sand was the one thing in endless supply. But it was unsuitable. Its wind-blown grains were too fine and smooth, and its grain size distribution was poorly suited to the controlled compaction of reclaimed ground. So the material came off the seabed. Calcareous marine sand, dredged roughly 11 kilometers offshore, from areas where the grain size matched the specification, almost 100 million cubic meters of it. Dredgers brought it in. Part was delivered through pipelines. In the shallower areas, the sand and water mixture was sprayed out in a powerful arc, a method known as rainbowing. The island grew out of the water layer by layer. Dredgers followed satellite positioning with differential corrections, allowing them to place the sand with centimetre-level accuracy. Out in open water, there is nothing to line your eye up against. Vibrocompaction solved the vertical problem, getting the ground to carry load and settle less under it. It could do nothing about the other threat. The sea does not press down on the island. It hits it from the side and carries the sand away. You can compact the foundation all you like. The waves will still chew at the edges. So a protective ring was built around the island, a rock breakwater about 11 kilometers long. It is layered. Inside, a core of sand and smaller rock. Outside, facing the open sea, armor of large blocks quarried in the north of the country, around 7 million tons in total. The blocks are not bonded with mortar, and the gaps between them are deliberate. An incoming wave loses energy passing through those gaps instead of slamming into a solid wall. Underneath the rock, engineers laid geotextile. It lets water through but stops currents from washing sand out from beneath the mound. Otherwise, the armor would settle into its own foundation. The breakwater came at a price. It restricted more than the waves. It also restricted the exchange of water between the sea and the space inside the palm. And that water needs to move. The longer it stays inside the lagoon, the longer heat, nutrients, and pollutants stay with it. That raises the risk of water quality problems, and for a residential district built right on the water, the risk is serious. Hydrodynamic modeling showed that zones with long residence times could form between the fronds. So 2 openings were included in the crescent, each about 150 meters wide. They improved circulation noticeably. They did not make it uniform. The outer areas flush faster, while between some inner fronds, water can linger for more than 2 weeks. A lot of confident claims have built up around this island, and most do not hold up under scrutiny. It did not turn sand into rock. It is still sand, packed far tighter, and brought up to the required bearing capacity. It did not remove the water. Below the groundwater line, the fill stays saturated. What changed is the ratio between grains and pores. It did not do away with foundations. There is no continuous concrete platform under the island. Buildings still required their own engineered foundations, and some used piles. And it did not stop the sea. The shoreline keeps eroding, and sand has to be put back. In 2023, the first major beach replenishment took place, about 1.8 million cubic meters, 20 years on. So what about the claim that the island is still sinking, 5 millimeters a year? That figure appeared in 2009, citing satellite observations by Fugro NPA covering 2003 to 2008. But Fugro itself later said the results were taken out of context. Movements in those first years were under a centimetre per year, within expected natural settlement, and did not support conclusions about long-term movement. So 5 millimeters a year cannot be treated as a proven rate for Palm Jumeirah today. And this is the answer that gets lost in the argument over whether the island is sinking. In geotechnical engineering, the goal is not literal stillness. It is to keep settlement within design limits, and to stop different parts of the ground moving by very different amounts. On Palm Jumeirah, a large share of the potential settlement was triggered in advance, before the main construction. Vibrocompaction made the ground denser, raised its bearing capacity, and reduced further movement. It did not eliminate the need for foundations or future coastal maintenance. The engineers did not stop the island from moving. They changed its schedule, bringing forward a large share of the potential settlement before construction, while riding the fight with the sea into a future maintenance budget. Palm Jumeirah works not because it never moves. It works because that movement stopped being a surprise.